So I have a couple demos set up here. And so I have kind of two different boards set up for three different demos, okay? So here there is an NXP RT685. That's a Hi-Fi 4 DSP. We're gonna do some automotive playback on that. There's another Cortex M7 here. We're also gonna do some automotive playback. And we can also do AEC demos and trigger word demos. And then there's another M7 here, which is going to do AVAS, which is sound synthesis for electric vehicles. And then I have an iPad here, which is kind of analog source of audio for some of these boards. And you can see loudspeakers here. So I'm going to start off here with an automotive playback example. And so basically the entertainment audio starts on the left side. So there's three stereo sources. And so this could be AM, FM radio, this could be Bluetooth, this could be audio from the head unit and so forth. Gets mixed together to stereo. And then we go through tone controls, left-right balance. It goes into speed-dependent equalization. I'll tell you a little bit about that some more. There's a volume control. So this is loudness control. Down here we have simulation for announcement channels. So that might be your navigation system, or it might be some kind of blinker sounds that get mixed together. And then we upmix to 7.1 channels. We have a fader subsystem, and then we go into kind of 8 channels of output processing. So you'll see there is a 6th order EQ for each one that you can configure. There's delays, gain, limiter, so to minimize distortion, some mutes, and then it goes out the output pin. So this is kind of typical automotive system for a kind of mid-level, entry-level system with 8 channels. And right now I'm on the PC. And so I can hit build and run. And are you able to hear the music?
Yes.
Yes, I can. Yes, I can.
Yep, so here we got a WAV file playing piano music. And then I can come in here and I can change the volume control. It gets louder, softer. So this is all in real time on the PC. And you can see all the different output channels being processed. And then I could adjust the fader. So we could fade to one side. So you can see the right channels are getting louder, the left channels quieter. Fade to the left side. Okay. And so I could get a multi-channel sound card and just listen to everything, make changes in real time, and so forth. I'll just show you a little bit more here. So you have tone controls. You can configure how much boost you want. So more bass, less bass. Okay. Treble controls. You can change all your cutoff frequencies. Very easy. And then we have speaker EQs. You could configure each of your EQs. So you can say, hey, I want some peaking filters. I want to adjust some gain. Maybe I'll have a high shelf, turn down the gain, and so forth. And so I'm hearing all these changes in real time. Okay. It's also possible to look at frequency responses, so I can see what's happening with the EQ and everything. On the PC, I can also record the output if you want to make a recording of the processing to hear the result and everything. Okay, I'll just stop the processing. What we also have is these are subsystems. So for example, this does loudness control. And what you'll see is this is the volume setting. So this is from like -100 to 0. And now you can specify your bass boost. So initially I do 0 dB, and then at -17 I start boosting up to a maximum of 15 dB. And then you can just change all your control points and stuff, move stuff around. Yeah. And then this is a controllable filter. Yeah. So you can start building up more sophisticated functions here with the system. So what I'll do now is I'm going to go ahead and change this design, or I'm going to connect from my PC now. I'm going to connect over USB, and I'm going to connect to an H747 board. So you'll see this is a Cortex M7, and this is the board right here. So this is an M7, and so I'm connected over USB here, and this says analog in, analog out. So let's take the same design here and then build and run here. And so now it's going to download over USB, and now everything is running here over USB. Let me plug in the speaker here. Okay. So this is all running. Let me make it louder. And now we can see all the signal levels. You can look at the input-output levels. And so this would be running, for example, on your amplifier or your electronics. And then you can make changes, and then you can listen in real time. And so this is on the M7. So you can see the total CPU usage. So this is measured on the target. And what's nice also is I can also do a detailed profile. Okay, and so now this will show you on a block by block basis exactly how many clock cycles it takes, how much memory it takes, okay, what percent of the processor. And then you can export to file. I'm just going to save this. And then it opens up here in Excel if you want to do more analysis of the data. You can see the total memory usage is 17K words. So 17 times 4, about 70 kbytes of data space. And so you can go through and then see exactly, you know, the volume control takes 4.9 megahertz. Okay. And then you can see each of these things, how much processing it takes. And so as you're putting together the system, it'll show you the cost of each of your features. And then you can do a careful kind of analysis. And the magic of AudioWeaver is I can take this design now, and let's switch to another processor. Okay, let's go to the RT processor. Okay, it sees a processor, it's a Hi-Fi 4. Okay, so this one's running at 594 megahertz, has 48 kilohertz sample rate. And now we're running on the RT. And again, everything works just like before. And so this one, since it's a DSP, it's more efficient. So rather than 25%, it's about 13% running here. And then we can do the same thing with profiling and so forth. What you can also do is you can very easily come here and then you can change the block diagram. So let me add a few more modules. Okay, I'm going to add a rebuffer module and a sync module. So this will allow me to inspect waveforms while it's running. And so right now we're running at a block size of 96 samples at 48 kilohertz. So this is 2 millisecond block size. And let me have it buffer up to a 10 millisecond block size. So now I'll be able to see kind of 10 milliseconds of data. And then in a couple of seconds, I have the new design running. Okay, and now I can look at the signal levels while it's running. So I can see time domain data. I can look at frequency domain data. I can show it in dB. So you can start analyzing your system and visualizing it. So this is one of the key features. Okay. So what happens is the PC is basically the graphical designer, and then use the inspectors for tuning. And then on the target, we have the libraries built into the target. So on my Hi-Fi DSP or my M7, I have the AudioWeaver libraries running. And then there's code outside, which we call the BSP code, the board support package. So we interface to the A to D and D to A converters, and then we pass the data in and out. And then there's a tuning API, which in this case is USB HID. And so we have a fixed set of libraries, and then the PC tools configure it, and then it sends down a data description. And let me find a slide here on dynamic. Okay, dynamic instantiation. So what happens is the signal flow and the tuning parameters are actually a data file. And so you store that data file on the final amplifier or your head unit, and then together the libraries plus the data file gives you the signal flow. And what that allows is I can very quickly build the system. So when I hit the button, it pretty much downloads the system. And so I'm not generating code. I'm not, recompiling, linking, downloading code. All it's doing is it's downloading data to the target. And so that's the dynamic instantiation. And what's really nice is, all your audio engineers don't have to have the development tools, okay? So for example, if you're programming a Shark or a Hexagon, you need specialized tools from Analog Devices or Qualcomm. So your firmware integration team needs the tools, but then the audio engineers will just use AudioWeaver, and then they don't have to keep reflashing the tools and reflashing the board. So I'm going to switch to the other sensory board. So I'm just going to unplug the one board and then plug this one in. And let me just change to the other board. Okay. So what this is a AVAS system, and they're typically designed to take data from the CAN bus, like vehicle speed, torque, acceleration. And what we end up doing is we end up modulating wave players. So there's 6 wave players here. For each one, we can specify a playback speed, we can specify gain, and then do calculations based on different variables. And so each wave player has a different set of PCM data, and then we can scale and then add it together. And then there's additional filtering. I think there's some upsampling, compressor limiters, and so forth. So let me go ahead and get this started. So this will build the system, downloads all the modules, all the wave data. And so now it's running. And there's a little drive simulator. So I have a gas pedal here. So it's easy to update the wave files, make changes, and so forth. You can turn the gain down a little. And then a lot of customers will get fancier, so they'll do some non-linearities, okay? Or have, when the torque is higher, make it more nonlinear, and so forth, okay? And then in the production system, instead of having a gas pedal simulator, we will get the data from the CAN bus, And then you can also kind of view the CAN bus data in real time as well, and then verify that everything's working correctly. And so this is all running on the M7, and this is 11%. So this will easily fit on, either a small processor, or maybe you want to run this under a safety operating system like QNX. So it's not that much processing. You also get the block diagram, so you can update, put different WAV files in there if you want, and so forth. And again, I could take this and simulate on the PC. So you could have a team trying new designs on the PC, listening what it's like, okay? You could even have it read CAN data from a file and then use that in real time. And so you could do simulated kind of different tours of the vehicle. And then be able to listen on the PC. You can record the outputs and share with people. So a lot of flexibility here. And we have starter block diagrams. We also have a team in Germany that if you want to have a unique sound, we can help you engineer that too. Okay, so this is my favorite. So this is an echo canceller demo. So let me go ahead and run the demo, and then I'll show you, kind of explain how it all works. And so this will run on the H7 board. And the H7 board that we were using, it has a microphone array on it. So if I go all the way to the bottom here, you'll see that there's a microphone array. So this is our linear microphone array. So we're using that for the audio input. And let me go ahead and start this. Okay. So this also has a sensory trigger word. So this is for voice user interface. And if I say Alexa, Alexa, you can see it triggers Alexa, Alexa, and then it'll count for you. What I can also show is the black signal is the microphone signal, and the blue one is after the echo cancellation. So in the blue one, you'll really only see my voice in the blue one. And so the difference between the black and the blue, if I subtract the two, that tells us how much echo cancellation I'm getting. So let me go ahead and open this, and let me go play the music. So make it a little louder here. So we're getting 40 to 50 dB of echo cancellation. Alexa, Alexa, Alexa. Can make it really loud. Alexa, Alexa. And then if I turn it off, Alexa, Alexa, doesn't hear me. Alexa, I have to shout. I turn it on, and I can whisper, Alexa, Alexa. Okay. So let me go ahead and just walk you through how this works. So let me start on the left side here. So basically, there's 8 input channels. So there's 2 USB audio, 2 analog audio, 4 microphones. And then we take one of the microphone channels, convert to floating point, and then we decimate by 3. So we go from 48 kilohertz to 16 kilohertz. So you can see that here. So it's 16 kilohertz, 160 samples. So that's 10 milliseconds of data. High pass filter, and then we go into the frequency domain using a filter bank. So this is the microphone signal. And on the bottom, we do the same thing for the reference signal. So it's coming through here. There's a gain control. This blue signal is the bell sound. And then we decimate into the frequency domain. And then we go into the subband module here. So this is a Kalman high performance echo canceller. So you can see, over 40 dB of cancellation. And then I can adjust this, how many taps I want. And so since my input block size is 10 milliseconds, each tap is 10 milliseconds. So this is 160 millisecond echo tail. For a car, maybe you need 100, maybe you need 80. But it's very easy to adjust this at runtime. So we go into the echo canceller, and then this outputs the error signal. So it's essentially the microphone minus the reference. Then we go through stationary noise reduction. So we call it single channel noise reduction. Back to the time domain. And then the rest down here is we go to the sensory trigger word. And so this has the Alexa trigger. And then here we can take unprocessed microphone or processed signal, gain, and then here we count the triggers. So this counts how many triggers we have. And then down here we have a little wave player. So if you look at this, this essentially is configured with the wave file. You can see bell.wave. And then whenever he triggers, he plays the bell. I can adjust the level of the bell, and then that feeds back to the input. And then everything else is just for plotting. So I can compute RMS levels of the microphone, and then after the AEC, convert to dB, and then this is just for visualization. And then here, I'm taking it out and then sending it out to the output pin. These channels are the music playback, and then this is the processed audio. So I could send that back to the PC over USB. And so we can make recordings of the output signal.